Here are a few questions from the unit angular momentum. See the first question, the components of L. What is the value of orbital angular momentum? L equal to R cross P. Here L is a vector. You may express L in terms of I into Lx plus J into Ly plus K into Lz. R is the position vector I into X plus J into Y plus K into Z. P is our momentum vector I into Px plus J into Py plus K into Pz. X component of momentum is h cross by into dou by dou x. Y component is h cross by into dou by dou y. Z component is h cross by into dou by dou z. Just we have taken out this h cross by outside. Then we have added the r cross p value ijk x y z. Then dou by dou x, dou by dou y, dou by z. Px, py, pz. These are all the values. Then instead of L, we have written this. Multiply and equate the coefficients of I, J, K. We can get the values of Lx, Ly and Lz. Here h cross by I is modified as minus I h cross. We know that minus I h cross dou by dou z is Pz. Minus I h cross dou by dou y is Py. So this is modified as y Pz minus z Py. In the same manner, we have written all other things. Then the square of the angular momentum commutes with one of its components, but the components among themselves do not commute. Lx, Ly equal to IH cross Lz. Ly, Lz is IH cross Lx. Lz, Lx is IH cross Ly. But Lx, Ly and Lz are commuting with L square. We know that L square is Lx square plus Ly square plus Lz square, which is our L dot L. Then Lx, Ly equal to IH cross Lz. You have proved this. For that, Lx, Ly minus Ly, Lx should be calculated. Lx operator is this much. Ly is this much. Multiply these two things. Minus into minus plus. Then I square is minus 1. H cross into H cross square. So minus H cross square. Write down this y as such. This dou by dou z is operating on this z. The value is 1, then remaining this dou by dou x is present. All other terms are 0. In the same manner, the value of Ly, Lx is this much. Then Lx, Ly minus Ly, Lx is this much. Take this h cross square outside. Then expand this h cross square in terms of plus I h cross into minus I h cross. Then combine these two terms. That is our Lz. So the net result is I h cross Lz. In this way, you may prove all other cases. What are ladder operators? L plus equal to Lx plus ILy, L minus equal to Lx minus ILy are called ladder operators. L plus is raising operator, L minus is lowering operator. The raising and lowering operators are called ladder operators. Each time operation with the raising operator increases the eigenvalue of the system by 1 unit of h cross. On the other hand, lowering operator decreases the eigenvalue by 1 unit of h cross. What is the value of z component of angular momentum in spherical polar coordinates? Lz equal to minus IH cross dou by dou pi. Now, eigenfunction sin m pi is given to you. You are expected to verify whether this is an eigenfunction of Lz or not. If minus IH cross dou by dou pi is operating on sin m pi, we can get another one eigenfunction, that is cos m pi. Therefore, it is not an eigenfunction for the operator Lz. What is meant by total angular momentum? J equal to L plus S is our total angular momentum, which is the summation of orbital and spin angular momentum. The total angular momentum obeys all the commutative relations as obeyed by L. What is meant by spin angular momentum? An electron in an atom possesses an intrinsic angular momentum in addition to orbital angular momentum. The intrinsic angular momentum S is called spin angular momentum, whose projection on the z-axis is m suffix s into h cross. The value of m s is plus or minus half. These are all the components of Sx, Sy, Sz. These are all Pauli spin matrices. This is sigma x matrix, this is sigma y matrix, this is sigma z matrix. Therefore, Sx equal to half h cross sigma x, Sy equal to half h cross sigma y, and Sz equal to half h cross sigma z. In general, S equal to half h cross sigma. What are the properties of Pauli spin matrices? They are 2 by 2 in dimension. They are even matrices. They are anti-commuting in nature because sigma x, sigma y equal to minus sigma y, sigma x. Therefore, sigma x, sigma y plus sigma y, sigma x equal to 0. The same condition is true for all other cases also. If you take the square of this sigma matrix, the value is 1. Sigma x into sigma x, if you multiply the sigma x matrices, sigma x into sigma x equal to 1, 0, 0, 1. We can get unit matrix, that is equal to 1. The eigenvalues of sigmas are plus 1 and minus 1. Since their squares are unity, these Pauli spin matrices are Hermitian in nature. If sigma y dagger equal to sigma y, then sigma y is Hermitian. Sigma y dagger means conjugate transpose. This is sigma y matrix. Find out sigma y star. Y star means change the sign of I. This minus I is changed into plus I. This plus I is changed into minus I. Then make the transpose. Convert a column into a row. Now we can get the same sigma y matrix. Therefore, we can say Pauli spin matrices are Hermitian in nature. Commutative relation. Find out the commutative relation between Jz and J plus. Jz J plus is H cross J plus. Jz J minus is minus H cross J minus. Here Jz J plus equal to Jz J plus minus J plus Jz. Jz, the value of J plus is Jx plus Ijy minus J plus value is Jx plus Ijy into Jz. Then multiply Jz Jx plus I into Jz Jy minus Jx Jz minus I into Jy Jz. Then combine these two terms. Jz Jx minus Jx Jz plus I into Jz Jy minus Jy Jz. This Jz comma Jx inside the square bracket plus I into Jz comma Jy. This is our IH cross Jy plus I into this is minus IH cross Jx. Then I into I square minus 1 minus and minus plus. So IH cross Jy plus H cross Jx. Take this H cross outside. We can have our Jx plus Ijy. That is our J plus. So the result is H cross J plus. The same way we may prove the second condition also. Now see the commutative relation. J plus J minus equal to 2H cross Jz. For that, J plus J minus equal to J plus J minus minus J plus J minus. Then this is our J plus value. This is J minus value minus J minus into J plus. Multiply and then simplify. We can get 2H cross Jz. Prove the following. Sx Sy equal to IH cross Sez. This is Sx Sy minus Sy Sx. Sx equal to H cross by 2 into sigma x. Sy equal to H cross by 2 into sigma y. Multiply, we can get this. Then find out the value of Sy Sx. That means this value into this value. We can get this. So Sx Sy minus Sy Sx is this much. If you simplify, we can get IH cross square by 2. This is modified as H cross by 2 into IH cross into this value. We know that Sz equal to H cross by 2 into sigma Z equal to H cross by 2 into 1, 0, 0 minus I. So H cross by 2 into this much is Sez. Then take out 1 IH cross outside. So the total result is IH cross Sez. In this way, we may prove the second condition also. Eigenvalues of J square is J into J plus 1 H cross square. Eigenvalue of Jz is Mz into H cross. Matrix form of J square is J dash M dash J square Jm, J into J plus 1 H cross square, del of J comma J dash, del of m dash comma m or m comma m dash. Here m dash equal to m dash equal to m. This Kronecker delta value equal to 1. If m equal to m dash or m dash equal to m, del of m comma m dash or del of m dash comma m equal to 1. Then matrix form of J Z. The eigenvalue of J Z is m z h cross. Here we have tried del of j comma j dash or j dash comma j, del of m comma m dash. If m dash equal to m, then del of m dash comma m equal to 1 or m comma m dash equal to 1. Eigenvalues of j plus and j minus. Say this is the eigenvalue equation for j plus. J plus into psi of j comma m equal to n plus into psi of j comma m plus 1. The n plus value is j into j plus 1 minus m into m plus 1. The eigenvalue of j minus n minus is j into j plus 1 minus of m into, the only difference is change this sign, plus into minus, m into m minus 1 minus m into m minus 1. If you simplify this, you can get n plus equal to j minus m into j plus m plus 1. N minus equal to j plus m into j minus m plus 1. This is the value of n plus, this is n minus. Then matrix form of j plus is this value into del of j comma j dash. This eigenvalue equation is represented. This eigenvalue equation is represented in this matrix form. J dash comma m dash j plus jm is equal to this eigenvalue into del of j comma j dash del of m dash comma m plus 1. For j minus, the matrix form is this much, del of j comma j dash del of m dash comma m minus 1. If m dash equal to m minus 1, if m dash equal to m minus 1, del of m dash comma m minus 1 is equal to 1. Here, if m dash equal to m plus 1, del of m dash comma m plus 1 equal to 1. In the case of jx, j plus equal to jx plus I jy, j minus equal to jx minus I jy. Add these two things, j plus j minus equal to 2jx. Then jx equal to jx plus j minus whole divided by 2. So eigenvalue of jx is eigenvalue of j plus eigenvalue of j minus whole divided by 2. Then eigenvalue of jy is, find out j plus minus jy. J plus minus jy is 2i into jy. Then jy equal to j plus minus j minus whole divided by 2i. Eigenvalue of j plus minus eigenvalue of j minus whole divided by 2i is eigenvalue of jy. These are all the matrix forms of jx and jy. Now we have to find out the explicit form of angular momentum matrices. Suppose j is given to you. Say for example, j is 3 by 2. M can have 2j plus 1 values. That is 2 into 3 by 2 plus 1, which is equal to 4 values. What are the values? Plus j, j minus 1, j minus 2, last value is minus j. M is having the value from plus j to minus j in steps of unity. Therefore, the possible values of m are 3 by 2, 1 by 2, minus 1 by 2, minus 3 by 2. These are the four possible values of m. J dash is always equal to j. M dash is also having the same value, 3 by 2, 1 by 2, minus 1 by 2, minus 3 by 2. While writing our explicit form, we have to change the value of m row wise, m dash column wise. See here 2j plus 1, you may have 4 values of m. Therefore, the matrix is having 2j plus 1 rows and 2j plus 1 columns. That is 4 rows and 4 columns. For j equal to 3 by 2, j equal to 3 by 2, the matrix order should be 4 by 4. Then the explicit form is j dash m dash. Here operator we do not know. That may be j square, jz, or j plus, j minus, jx, jy, whatever it may be. Jm. This is the explicit form. Then j dash is always equal to j. M dash is varying from plus j to minus j. The same is true for m also. M dash is varying from plus j to minus j. So first take this plus j value, m dash. Then j, write down as such j, m. M is also having the same value, that is varying from plus j to minus j. J minus 2, j, j minus 1, j minus 2, minus j. These are the possible values of m. Put the value of m is equal to j here. Now, we have to fix the value of m dash as j throughout this row. But m is changed. First value of m is j, second value of m is j minus 1, j, 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 j minus 2, then j, 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 j minus 3. That's all about the matrix. See here, this is m dash, this is m. Throughout the row, the value of m dash is j, but m is changed, j, j minus 1, j minus 2, j minus 3. Now write down the second row. Here j, then m dash value is j minus 1. Throughout the row, this value is j minus 1. M value is varied, j, j minus 1, j, j minus 1, j, j minus 1, j, j minus 2, j, j minus 1, j, j minus 3. Then third row, j, j minus 2, j, 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 j minus 2, j, j minus 1, j, j minus 2, j, j minus 2, j, j minus 2, j, comma, j minus 3. The last row, j, j minus 3, j, 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 j minus 3, j, j minus 1, j, j minus 3, j, j minus 2, j, j minus 3, j, j minus 3. See here, the value of m dash, this is m dash. M dash is changed column wise. J, j minus 1, j minus 2, j minus 3. M is changed row wise. J, j minus 1, j minus 2, j minus 3. Throughout the row, the value of m dash is j. Throughout this row, the value of m dash is j minus 1. Throughout the third row, the value of m dash is j minus 2. Throughout the fourth row, the value of m dash is j minus 3. But the value of j is changed. But column wise m dash is changed. This is called our explicit form of angular momentum matrices. For simple case, if I write, you may understand more. Say for j equal to 1 by 2. If I write j equal to 1 by 2, you may understand. J equal to 1 by 2, the possible values of m equal to plus j to minus j in steps of unity. That is plus of, and another one value is minus of. J is equal to j dash. M dash is also plus of and minus of. The skeleton is j dash, m dash, j m. Here the operator is coming at the middle. Now this is equal to j dash is equal to j, that is 1 by 2. First keep the value of m dash is half. J is always equal to j dash. M is half. Then 1 by 2, m dash is half. And j is half. M is minus half. Then here j dash is half. M dash is minus half. J is half. M is half. Here half. M dash is minus half. J is half, m is minus half. See here, this is m dash. M dash is changed column wise, plus half, minus half, m dash. But this is m. This is also m. This is m. This is also m. Here m is changed row wise. Now, if you want to find out the angular momentum matrix for j square, j dash, m dash, j square, jm, the condition is j into j plus 1 h cross square del of j comma j dash del of m dash comma m. If m dash equal to m, del of m dash comma m equal to 1. See the places. Here m dash equal to 1 by 2. M equal to 1 by 2. So the element is present. Element. Here m dash is 1 by 2, m is minus half. This condition is not satisfied. M dash not equal to m. Therefore no element, 0. Here m dash is minus half, m is plus half. M dash not equal to m. So no element, 0. Here m dash is minus half, m is minus half. So m dash equal to m. This condition is satisfied. So element is present. What is the value of element? We have to find out. Here m dash equal to m, this is 1. J is always equal to j dash, this is also 1. So element is j into j plus 1 h cross square. 1 by 2 is the value of j. 1 by 2 into 1 by 2 plus 1, that is 3 by 2. 3 by 2 into 1 by 2, 3 by 4 into h cross square. So the j square value is j square matrix for small j equal to 1 by 2 is 3 by 4 h cross square 0 0 3 by 4 h cross square. This is the j square matrix. J square matrix for j equal to 1 by 2. J square matrix for j equal to 1 by 2. is 3 by 4 h cross square 0 0 3 by 4 h cross square. Now we have to find out the J square matrix for J plus matrix for J equal to 1 by 2. Now we have to write the eigenvalue equation for J plus. Eigenvalue equation for J plus is J dash M dash J plus Jm, which is equal to root of J minus M into J plus M plus 1 del of J comma J dash del of M dash comma M plus 1. Here J dash M dash J plus Jm equal to, now write down the matrix, J dash equal to J 1 by 2, M dash is 1 by 2. Then leave out this operator, the value of J is 1 by 2. The first condition for M is 1 by 2. Then J dash equal to 1 by 2, M dash is 1 by 2, J is 1 by 2, and M is minus half. Here half minus half, 1 by 2, 1 by 2, 1 by 2 minus 1 by 2, 1 by 2 minus 1 by 2. See this matrix? Here, this is M dash, this is M dash, this is M dash, this is M dash, this is M, this is M, this is M, this is M. J dash is always equal to J. See here, M dash is changing column wise, plus half, minus half, plus half, minus half. M is changing row wise, plus half, minus half, plus half, minus half. Now, where the element is present, that is a question mark. If M dash equal to M plus 1, if M dash equal to M plus 1, del of M dash comma M plus 1 equal to 1, element is present. Otherwise, there is no element. See here, M dash is half, M is half. Here, M dash equal to M. So, no element. 0. Here, M dash is half, M is minus half. Minus half plus 1 plus half. So, the condition is satisfied. Element is present. Here, M dash is minus half, M is plus half. M dash equal to M plus half, that is the condition we expect. 1 by 2 plus 1, 3 by 2. Minus 1 by 2 not equal to 3 by 2. So 0, no element. Here M dash is minus half, M is minus half. Minus half plus 1 plus half. So the condition M dash equal to M plus 1 is not satisfied. So no element, 0. Only at this place the element is present. What is the value of the element? We have to find out. Using this, we have to find out the element. If M dash equal to M plus 1, this value is 1. If J equal to J dash, this value equal to 1. So that to find out the element, use these terms. 0, only here the element is present. What is the value of J here? J is always 1 by 2. 1 by 2 minus M value. Here the M value is minus half. So minus into minus plus 1 by 2 into J value is 1 by 2 plus M. M value is minus 1 by 2 plus 1. 1 by 2, 1 by 2, 1. All are present inside the root. 1, 0 plus 1, 1, root 1. So this element is 1. So this is the angular momentum matrix for J plus, for J equal to 1 by 2. For J equal to 1 by 2, the value of J plus is 0, 1, 0, 0. In this way, we have to find out all other matrices. j square, j plus, j minus, jx and j plus, jx and jy. Now, what is Kapskadan coefficient? It is possible to go from one coupled representation to another uncoupled representation by means of a transformation coefficient called the Kapskadan coefficient. This is coupled form. This is in the uncoupled form. M equal to M1 plus M2. J equal to J1 plus J2. See, J comma M. These are all in terms of J1, J2, M1, M2. These are all uncoupled. These are all coupled. We are transforming. We are expressing the coupled representation in terms of some uncoupled representation. For that, we need a coefficient. That coefficient is called CG coefficient. This is CG coefficient. What is a triangular rule? For a non-vanishing CG coefficient, the total angular momentum should satisfy the following inequality called the triangular rule. The value of J should be greater than or equal to J1 minus J2 and less than or equal to J1 plus J2. If this condition is satisfied, the CG coefficient is not vanished. Otherwise, the CG coefficient is vanished. This is written as J1, J2, J. This is equal to three sides of a triangle. Therefore, we are calling this one as a triangular rule. Otherwise, the CG coefficient is vanished. The value of J should be greater than or equal to J1 minus J2, modulus of J1 minus J2, less than or equal to J1 plus J2. Otherwise, the CG coefficient vanishes. Therefore, we are calling this one as a triangular rule. What are identical particles? Particles that can be substituted for each other with no change in physical situations are called identical particles or indistinguishable particles. Electrons, neutrons, protons are called identical particles. What are symmetric and antisymmetric wave functions? The parity operator tells us whether the wave function changes its sign or not on inversion of coordinates. On inversion of coordinates, if there is no change in the sign of the wave function is said to be symmetric. Suppose if you inverse the coordinates, psi of x, y, z is equal to psi of minus x, minus y, and minus z. There is no change in the sign of the wave function. Such a wave function is called symmetric. If psi of x, y, z equal to minus psi of minus x, minus y, minus z, then the wave function is antisymmetric. On inversion of coordinates, if there is a change in the sign of the wave function, it is said to be antisymmetric. The particle exchange operator is nothing but our parity operator. Say this is the eigenvalue equation of particle exchange operator P12 or pi into psi of 1 comma 2 equal to lambda into psi of 2 comma 1. This is the eigenvalue equation. If you allow the particle exchange operator once again, P12 square is into psi of 1 comma 2 equal to P12 into psi of 2 comma 1. Both sides we are operating P12. Here P12 square into psi of 1 comma 2 equal to P12 lambda into psi 2 comma 1. P12 into psi of 2 comma 1 is once again lambda into psi of 1 comma 2. So lambda into lambda, lambda square. So this is equation 1. If you use the property, particle exchange operator changes the coordinates. 1, 2 is changed as 2 comma 1. This is property. If you apply the second time operation on this, that is 2 time operation, then we may get psi of 1 comma 2. P12 psi of 1 comma 2 is psi of 2 comma 1. Another one time P12 operation changes psi of 2 comma 1 into psi of 1 comma 2. From the equations 1 and 2, lambda square is equal to 1, not plus or minus 1. Lambda square is equal to 1. Lambda square is equal to 1. Therefore, lambda equal to plus 1 and minus 1. If lambda equal to plus 1, now come to this P1 to psi 2 comma 1 equal to psi of 2 comma 1. Even parity we can get. That is, the wave function is symmetric. Suppose lambda equal to minus 1, psi of 1 comma 2 equal to minus psi of 2 comma 1, odd parity. So the wave function is antisymmetric.